Welcome to ECE243 Lecture number 15. Here we are doing an asynchronous lecture. It brings back memories of pandemic teaching, but I'm recording this just after having given lecture 14. We are on an interesting journey, trying to understand this interrupt mechanism, which, as I've mentioned, has quite a bit of complexity. And this is the third lecture of 3, in which I will tell you everything you need to know and give you some example code that will help you do Lab 4. Lab 4 is next week. So let's begin by showing you all of this. This is actually a review of essentially lecture 14 and 13. And let me go through it quickly, but you can, of course, pause this and look at it slowly if you wish. So the point of interrupts is to have a very organized way to deal with external events to the CPU that are coordinated very well. And the example we've been using of an external event is, say, a button press. Somebody presses and releases a button, and we would like to react to that, like you did in Lab 3 using polling, except now in this more organized fashion. But other events include things like, also in Lab 4, the timer has counted down to 0, and you want to know that it's counted down to 0 and that a certain amount of time has passed. But of course, it could be a keyboard press. You pressed a key on a keyboard, clicked a mouse, got a message on the internet. That could all cause an interrupt, as could some other things that happen in software, and those are called, more broadly, exceptions. So that's what I was talking about here. And the basic picture, once again, is to think of the processor as executing a main program, and the event happens. And the event we're going to stick with is a button press as an example of something that we would want to cause an interrupt. So a button press happens when this code is executing over and over again. We don't know what this code is, as I represent it here. You press a button, and by the end of this lecture, you'll have some sense of how to make that actually happen. If that happens, then we need to stop executing this. So the hardware does stop executing this, and it transfers controlled through some mechanisms I've told you about already to the interrupt handler, which would then do things to respond to that button press or perhaps other interrupts. Once it's finished responding to that interrupt, we need execution to return back to the statement following the one that was finished when the interrupt occurred. And I keep saying that it must go back here as if nothing had happened to it. None of the registers or condition codes or anything that this program relied on must have appeared to have changed, so that this program can still continue executing, doing whatever it was doing. So that's what I've been talking about for a couple lectures now. We talked about that we need to return to the right place, and that was done by, I think at the very end of the lecture, we talked about the program counter being restored to what it was supposed to be. We talked about the condition codes, Z, V, N, and C, need to be restored to what they were at the moment of time when this instruction was finished executing. And I taught you about how the current processor status register gets saved in something called the save processor status register _IRQ. That is, we switch to the IRQ mode of the processor, and in doing so, the hardware saves the old CPSR into a SPSR. And by the way, that meant in that last lecture I wrote down in both lectures, I talked about the different modes of the processor, and the supervisor mode, the user mode, and the interrupt request mode. And maybe the most important thing to understand there was that picture I drew on the board, and you can look at the notes for this in lecture 13, that the different modes bring in new versions of important registers, most particularly the stack pointer register and the link register. And we discussed last day why the new link register remembers the program counter, so we know where to go back to. And I've discussed that in order to know where to go here, you have to place a branch to this instruction in the exception vector table, so that when the branch, when the interrupt happens, the processor knows where you want it to go to start dealing with it. Okay, so that's all review. All right, now I want to jump into some set of details, and I'm going to, again, I'm layering these details. There are a lot of them, and so I'll just have to go at them one at a time. Where I want to go next is I want you to think about the interrupt handler. Let's consider the interrupt handler. The first, that's this routine right here, the first thing that responds to this interrupt request. It has two things I want to talk about. One is that the interrupt handler is the first point of contact after the interrupt happens, and there could be multiple sources of the interrupt. It could be that you pressed a button, or it could be that the timer timed out. And so the first job of the interrupt handler is to figure out which of those it is, and to send execution off to the right service routine to handle whichever one it is. The other thing it will also have it do is save all the registers that were being used by the main program and push it onto its own on the stack. And so, let me write some of that down. We're going to deal with figuring out the cause of the interrupt. Could be lots of things, as I say in the general case. In the case of Lab 4, we want to know, is it a button press or a timer that's caused us to show up here? And we wanted to save registers so the main the main program isn't disturbed. Remember, it has to be we have to return to it as if nothing had happened. And the other thing I want you to remember is when we arrive here, the processor will be set by the hardware to be in IRQ mode. So we'll be in IRQ mode, and that really means we have a different link register, which contains the return address of where we want to go back to, and a different stack pointer. And I'm not going to show it now, but later on I'm going to show you that before all this happens, you have to set up a separate stack with that stack pointer so that you don't interfere with the stack that's running in the main program. But we'll touch all that later. So this is what the beginning of the IRQ handler needs to look like. Well, the very first thing you should do is push register R0, oops, that should be like that, R0 to R12, and the link register, which is R14, onto the stack. Save all the registers, plus the link register on the stack. Why do we save these registers? Well, because main program was using them, we want to save them and restore them later. Why do we store the link register? Remember, that's special. It's the new link register, the IRQ link register. We are going to call some subroutines that would otherwise destroy this link register. So we need to save it so that we can restore it and then return from the interrupt correctly. So that's the first thing we do. And then we need to write code, which I'll show you later and talk about in more detail later, code to determine which device caused the interrupt. I'm not going to show you how that's done because there's more complexity I have to introduce first. But so I will kind of pseudocode it here. I will say, if it was the key key/buttons, excuse me, then do this. Branch and link to the key ISR, the key interrupt service routine. So we'll make a subroutine that does that. Excuse me. Else, if it was, and this is specific to Lab 4, if it was the timer, then branch and link to the timer ISR. So this, just to be clear here, this is specific to Lab 4. And in Lab 4, we only have interrupts coming from those two sources. And so there's an else here. Imagine you arrived here and you determined there wasn't a button pressed causing the interrupt and the timer didn't time out. Well, then something has gone terribly wrong. If you hit this location, and so you hope that you would never hit this, and so I don't know what to say here. Here's a non-executable statement. Freak out because something is wrong. This should not happen. We should not arrive here. And let me repeat why that's so. In Lab 4 specifically, you will set things up so that only the buttons and the timer will cause an interrupt. We haven't even got to how that's done yet. And nothing else. And so if you go through the thing that checks which one caused it, and you determine that none of them caused it, that means something's gone completely wrong. And you'll see in the code that I'll show you that we just go into an infinite loop. The freak out, how do you freak out? Well, you go into an infinite loop, like end, branch, end. And so, but normally you won't freak out, so all is good. And so what do you do next? You need to restore the registers so you can return to the main program. And we do that with a pop, exactly the opposite of what we had above. Pop R0 to R12 and the link register. So that gets the link register back from what it was. Did I use caps up there? Yeah, I did. Which is good. And now here's a complex instruction. The true name of the following instruction I'm about to give you should be called return from interrupt. Often processors have an RTI instruction, actually, that's exactly that. Meaning return to the main program. And yes, this next instruction doesn't quite look like that. It sort of does and sort of doesn't. And let me show it to you and then explain it, because it's a little complicated. It's a subtract with S on, where the destination of the subtraction is the program counter. And you put into the program counter the link register. I'm not being consistent with my caps here. Let's be a little more consistent. PC LR comma number 4. Now what this appears to do, it's a bit confusing. First of all, you have to remember that the link register that we just popped off the stack, that was as it was when we came in, contains the address that we're going to return to in the main program. That was a core element of lecture 14. And so what this does is the program counter gets the link register minus 4. You might go, well, why are we setting it to something different than what the link register is? Didn't the link register have the right address to go back to? Turns out the answer is no. For a weird reason that's not fun to have to explain to you folks. The architects at ARM actually don't have the program counter pointing to the next instruction. It points to the one after that, and they fix it up when they're just going to fetch the next instruction. So what gets saved into the link register is something that is in fact incorrect by 4. It's ahead by 4. So we have to take that 4 off. And it's very annoying to have to explain that to you because it doesn't make a lot of sense. You could say, why don't they store the right number? And gosh, I wish I knew the answer to that. But you do. But that's not all. This is actually a very special statement. It takes us back to where we were, but it's also important that we return from the IRQ mode back to the previous mode that we're in. And in the case of Lab 4, we'll be going back to the supervisor mode. So it turns out that you need to do that, and the ARM processor treats this instruction specially. It treats the instruction specially if the target, the destination, is the program counter, and this has an S on it. If those two things are true, then also, so let me write that down. Well, I'll say it, then I'll write it down. If you've got both those things in the instruction, this does one extra thing built into the hardware. It says, oh, this is actually a return from interrupt. And so in addition to doing this thing, restoring the PC to LR minus 4, I will take the saved processor status register, the SPSR underscore IRQ, that special saving register that has the old condition codes, the old modes, and other things, and I will restore that into the CPSR. So it's sort of a sub-piece. When this is the target, the destination, this is on, then the SPSR gets copied into the CPSR, the SPSR underscore IRQ. So when there's this S, that thing, and the PC is the target, this instruction also does this. It copies the SPSR underscore IRQ, that special register that recorded what the CPSR was at the moment of interrupt. Like we finished this instruction. You have to remember this now. We finish executing this instruction and we jump over here, but we copied the CPSR into the SPSR underscore IQ. And so this instruction copies the SPSR IQ into the CPSR. And it's that act that in this restores the condition codes, I, N, Z, etc. Not I, sorry. C, N, Z, etc. And the old mode, because it's taking the low order 5 bits and they get copied from the SPSR back into the CPSR, and it's that converts the mode back to whatever it was. If you were in the supervisor mode, you go back, you switch from the IRQ mode into the supervisor mode. You would go back, and since we're only going between supervisor and IRQ mode, we go back to the IRQ mode. And there's something, sorry, not IRQ, supervisor. Something kind of interesting here. There's nothing special that happens to go back to the mode. It is simply this act of copy, the old mode, the act of copying the SPSR into the CPSR does it. Because whatever's in the CPSR, that's what the mode is, and the processor behaves accordingly. So it's sort of interesting to see that. And I say it because ultimately we're going to show you more details about what's going on inside the processor. And this is just one register kind of being copied into another, but it causes all these other things to happen. It's all done, it's all under control of registers. Whoa, that's so yes, and now I have and let me just say, and the subtract 4 is a strange arm thing that has no good explanation. You just have to do it. Okay, so that's how you return from the interrupt. Okay. And I think that had enough complexity. That's why I isolated that out. Now, let's step back and look at the three parts of hardware involved in interrupts. And the story so far that you know is, well, there's the processor. And you know it talks to memory, but we don't care about memory at the moment. And we've taught you about the keys. You know, there's 4 of them. And also the timer. And I've taught you a little bit, like, sorry, maybe I should really draw this like that. You know, we talked to memory. We also talked to we've shown you that this is an I/O device, and so is this, and it has registers associated with it, which I'll talk about in a moment. And so I could draw, actually, don't copy this exactly. I just want to, because I'm going to erase this line. I could say, yeah, these things, we talked to these things with the same kind of connection. So there's this IRQ signal that both devices can activate. But that's actually not what happens in our system. There is a third player that is there for much more complex systems. It's a little unfortunate that we have to deal with this third player, but it is what's there, and we're going to try to, we will protect you from most of the complexity. There's a third player in here called the generic interrupt controller. And it's the one that's allowed to pull on the IRQ line, and the keys will ask the generic interrupt controller. They will send a signal to the GIC, that's what we're going to call it, to say, I wish to cause an interrupt if you've set them up properly. Similarly, the timer does that. And so the reason I'm bringing this up is this means there are 3 players. The I/O, for any given interrupt, the I/O device itself, the GIC, and the processor. And here's something that is quite standard across all systems. When you have players like this, you have to set everything up so that they all agree to do a part of their job. And you have to first tell the keys through one of the control registers in the parallel port that when the button is pressed and released, I would like the interrupt to be sent out, and it goes out to the generic interrupt controller. Similarly, the timer has to be told, don't just time out and set the F bit, cause an interrupt over this wire. And so you have to tell them to do that. But then you have to tell this thing, which is meant for controlling much more complex systems, that you want it to pass on requests from these 2 things, which is fine. But you have to do that, otherwise it won't. It'll get blocked and nothing will happen here. And even if you do that, the third thing you have to do is the processor itself has to say, keep an eye on this line and trigger an interrupt when it gets activated. The normal state of the initial state of the processor is to ignore all interrupts, and that's a good thing because you don't want it to go hunting through the exception vector table until that's set up properly, and things like that. So there's a way to prevent interrupts here. There's a way to prevent them here, or prevent them here, or conversely, in order to cause interrupts, you have to enable them here, and here, and here, and here. That's the big picture. Something like that is always true. There isn't always one of these. Sometimes these guys plug directly into the processor, we still have to know about this, and we're going to protect you from the complexity of this with one exception. Okay, let me write some of that down. So we could say it this way. The processor has just one interrupt request line. IRQ line. But there may be many devices that want to activate it. In this case, we have two, but it could be lots. Want to cause an interrupt. The GIC makes it possible to oversee all those devices and allows the processor to figure out which one is causing the interrupt. Oversees, that's in quotes, all these devices. And allows the processor to figure out which one is causing the interrupt. It will only trigger one interrupt, the GIC. Even if both of these are requesting an interrupt, it will request one, and then you will tell it, okay, I've got it, and then it will request another one for the other one. So we'll see how that works in a second. And what I'm talking about right now is the GIC is the one that you ask, which one caused the interrupt? If it was the key buttons, I'll do this. If it was the timer, I'll do this. So you'll see that in a moment. And I guess the other thing to say is there are three players, there are three entities, three things involved in the interrupt. Interrupts. One, the processor. Two, the GIC, because it's bringing things together. And three, the device itself, whether it's the timer or the push buttons or something else in other systems. And we need to enable interrupts. Enable interrupts. Tell them that, yes, we want this to happen in all three for interrupts to work. But you don't want to enable interrupts before you've set everything up that you're supposed to. And by default, initially, nothing is enabled. None of those three things is enabled. So here is how to set up interrupts in all three. I ultimately will show you the code, but I'm going to isolate out each thing and describe it because it needs describing to understand it. We will assume, which is correct in the case of your lab, that the processor starts out in supervisor mode. So we're allowed to change the CPSR as we wish. And we're interested in the mode bits, but there's some other bits in the CPSR related to whether or not the processor will pay attention to the interrupt request line or not. So let's talk about that first. So to enable interrupts in the processor, i.e. to have the processor respond to an interrupt request. Bit number 7 of the CPSR is the IRQ enable bit. Comma I. If it's a little bit backwards in that if I equals 1, interrupts are disabled. It's kind of the opposite of the way you normally do this. Don't know why. If you set I equal to 0, interrupts are enabled. And so let's look at the CPSR one more time. Because now we've learned there's more in it than we thought. Those top bits from bit 31, those top 4 are the good old condition codes that I keep talking about. The things that are set by any operation with an S at the end of it, like sub S, or a compare instruction sets these things, or a shift sets the C bits. Those are the top 4 bits. And then last lecture we discussed the bottom 5 bits is the processor mode. And now the next 3 bits, well, the one we care about is the I bit, which is bit 7. Bit 6 and 5 are called the F bit and the T bit. So the one we really care about here is this I bit. Very briefly, the F bit is enabling a different interrupt. There is another wire called the FIRQ, and it's the fast interrupt. And so we won't use that, but it's another one we could use. And the T bit is something completely different. It's for thumb mode. So it's an ARM processor. There's a simpler version of the instruction set that you can make happen. It's actually only 16 bits. And that's called the thumb instruction set. Thumb, get it? ARM, thumb. And so if you turn that on, you don't ever want to turn that on because all your code won't work because you don't know those instructions and you're not using those. So we really only care about the I bit here, and turning it to 0 enables interrupts. It means the processor will respond to anything, to an activation of the IRQ line if it gets activated. The GIC has to agree that it's going to activate it, and something has to tell the GIC. But this is why it's only step 1. To enable interrupts in S supervisor mode, we need to put the appropriate numbers into this CPSR. Well, so what is the supervisor mode? Well, supervisor mode is when these 5 bits are 1, 0, 0, 1, 1. So assuming we're in supervisor mode, we want to stay in supervisor mode. We always want this T bit to be 0. We don't want fast interrupts to be enabled, so we set that to a 1. But we do want regular interrupts to be enabled, so we set this to a 0. So this number needs to get into the CPSR, 0, 1, 0, 1, 0, 0, 1, 1. So we need to get this. Let's just do that. Into the lower 8 bits of the CPSR as follows. I taught you last lecture the move into the status register command. Looks like this. Move MSR CPSR _C. Remember, this just means the lower 8 bits, don't touch the rest of them. Comma number 0 B binary 0, 1, 0, 1, 0, 0, 1, 1. That's this number. So this tells the processor, I want you to stay in the supervisor mode and enable interrupts to happen, at least respond to them. Okay, that's only one of the 3 players. Let's go to the other player that you're already used to, these guys. Now let's just talk about this for a second. You know the keys. You did lots of things with them in Lab 3. You saw that the edge capture register goes to a 1 when you push and release the button of any given button, the corresponding bit in the edge capture register. You may or may not recall that when I showed you the 4 registers that oversee the push buttons, one of them was called the interrupt mask register. And it has 4 bits that mean when you turn them on that you want the keys to cause an interrupt when the corresponding key to the mask bit is on. So if you wanted all 4 bits, all 4 keys to cause an interrupt, you would put all 4 bits in the interrupt mask register to be on, and that is enabling. That's telling this device, I want only then, when I set that particular register, do I want you to cause an outgoing request, which is going to the GIC, to happen. If those mask bits are off, then that won't cause an interrupt. So let me write that down. We need to enable interrupts. In this case, I'm just talking about the push buttons. There's something similar for the timer, by the way. Out from, so I want to enable interrupts to come out from the keys. Keys 3 to 0, perhaps. And here I want you to recall the 4 memory mapped registers associated with the keys. Remember, there's 4 of them. The base address of the keys is 0xFF200050, and at that base address there is the data register. Remember, there's only 4 interesting things there. Tells you whether the button's up or down. Yeah. So that's the data register. You're very familiar with that from part 1 of Lab 3. At address 54 was we didn't use that one. That's the direction register. We don't need it. At address 58, I said, well, there's this thing called the interrupt mask register. Didn't really say much about it, but now I am. and then at address 5C is the edge capture register. And both of these have bits 0 to 3 that are relevant. And if you want key 0 to cause an interrupt when it's pressed and released, you set bit 0 of the interrupt mask register to be 1. And if you want the other ones to cause interrupts, you set them to be 1 too. So just like this kind of corresponds to that, the mask register corresponds to it. So to have key I, which is between 0 and 3, cause an interrupt, when it's pressed and released, you turn on bit I of the interrupt mask register. Complicated, eh? This is just step 2. Like I said, there's 3 players here. There's a processor, you've got to tell it to listen when there's an interrupt, and the device, in this case the keys, you have to say when the event that you're interested in happens, you must send an interrupt request. But then there's this nasty fellow in between called the generic interrupt controller, which has lots of setup, which you won't have to learn about. We'll just give you some code that does that. It also has to pass on that request from the device to the processor. You kind of see how that works in a second. However, to turn off a request from the keys, an interrupt request, once you've received it inside the processor itself, once received, you have to do what you did before. You have to write a 1 into the edge capture register. That turns off the edge capture bit, and that will turn off the request coming from the device. If you don't remember that, that's a key part of Lab 3. But you must write a 1 into the edge capture register. It turns off, it only turns off one thing, by the way. It turns off the request that would have been activated here. If this one still hasn't been responded to, this will still be going, I think. We'll talk about that in a second. Okay, so now we have to talk about how to get that third piece activated. The third piece is the generic interrupt controller needs to be configured. And it's pretty complicated, but let's just say that. We need to enable plus configure the GIC to pass on requests from its devices, in this case in Lab 4, the keys and the timer. The keys and the timer, or whatever. This thing is complex, and I haven't looked through the code that does that, and we will give you the code that does that, but it's too much to worry about because it's enough to understand that the requests get passed on, except for one thing that I'll explain in a moment. So configuration is too complex, mostly. And it's not needed to get the concepts. For you to get the concepts. The interrupt concept. So we give you the code to do it. The code in a subroutine called config GIC. So you just do this. You branch and link early on. I'll show you the code that does this to config GIC, and it does all the setup that I don't want to describe to you. However, there are two registers in the GIC that you do need to know about. One of them tells you what the cause of the interrupt was, whether it was the keys or the timer or something else. It answers that question I showed you earlier, who caused this interrupt? Because there's only ever one cause of one interrupt at a time. And another register you use to send a signal back to the GIC to say, I have seen this interrupt. You've yanked on my line, my IRQ line, and it has to keep activating that line until the processor somehow tells it, no need, I've now executed an interrupt. Based on that, please stop sending me an interrupt for that cause that caused this. If you have other causes, go ahead and keep doing it. I will come back and go through the whole process again. So there are two registers that help do that. So you do need to interact with two memory mapped registers, and hopefully you're getting used to that term, registers in the GIC. And I'll show you both, give you their names, and then I'll tell you exactly what they do. One at address 0xFFFEC10C has what's called it has 10 bits of interest, the bottom bits there. It is called the ECE243 and this stands for interrupt. That's not a great name. Interrupt acknowledge register. That's what the IAR stands for. And while we're there, we'll say what you see there, it's something you read, is an interrupt ID. And depending on the number that's in this register, when you show up in the interrupt handler, you can figure out who caused the interrupt. And then FFEC110 is something you write into the lower 10 bits, also an interrupt ID. It's called the ICC EOIR, and that stands for end of interrupt, which really sounds like an acknowledge to me, register. And so the ICC IAR tells you which device caused the current interrupt. In the low order 10 bits. If that number, which contains an interrupt ID, and if the interrupt ID is equal to 73 base 10, that means one of the keys caused the interrupt. The interrupt ID is 29 in base 10. It means the A9 private timer, the timer we've been using, caused the interrupt. And just, there's another timer which has the ID of 7210. It's the interval timer. And you'll see this, I think it might be talked about in the section 4, part 4 of lab 4, the optional part. So there's another timer, which is really it's another timer, and its interrupt ID is 72. So you read this register, you load or read this register to figure out who caused the interrupt coming from the GIC. The GIC sets it that way. And the other thing to know is that when you're to tell the GIC that the processor has seen the interrupt from a given device, like, say, the keys, from a device, you must write its interrupt ID into the other register. Write, which means store, its interrupt ID into the ECE243. It's like an acknowledgement. Yeah, that's why I don't know why it's called isn't called the acknowledge register actually. So and this tells the GIC to turn off that interrupt. Now, if two things were interrupting at the same time, this is a common question, here's what happens. Say both the timer has timed out and you hit one of those keys. The GIC will pick one of those and say, okay, I think I'm going to pass on, it doesn't matter how it picks at this level, I'm going to pass on that there was a interrupt from the keys. And so the code in the IAR will be 73. And you'll do stuff and respond to that interrupt. And then you'll write 73 into the ICC EOIR, and that will turn off, and notionally turn off the GIC's yanking on the interrupt. But it will then turn it back on again because the other device wanted to interrupt as well. And then when you will return, but you'll return from the interrupt, go back in the main program, and then you'll get interrupted again. And then you'll look at here, and there will be a different code. If it was the timer, the A9 private timer, it'll be 29 then that's here. So this system is set up so that only one interrupt gets serviced at a time. You have to return from the interrupt, go back to the main program, and let another one happen. You don't, at least in this simple world that we're in, we don't try to service two interrupts. You let let it all play out. I hope that makes sense. Okay, let's show you. Here's what I want to show you. Let's show you this program. Let's make it as big as that so it covers everything up. Here's the program that I'm going to give you. This program's purpose is to do what was done. I demoed something very similar when I was showing you polling. Remember, I had a simple program that would poll the buttons, and every time I pushed and released the button, it would turn on LED 0, and then when I pushed and released the button again, it would turn off LED 0. And I pushed it again, it would turn it on. So it would just go on and off. I gave you that program a couple weeks ago. Here I'm going to make a program that has the identical functionality, except the difference is the push and release of the button is going to cause an interrupt, and I have to set up everything I've described to you to make that happen. So I'm going to demo that program in a second. Actually, maybe I should demo it. So here's that program. I'm going to compile it, run it. It starts by turning on the LED, and whenever I click a push button on and off, it turns it off. You can kind of see the main loop here is doing kind of nothing, and you can't actually see anything happening. So let's just stop that, and let me kind of talk to you about the program itself. Here's the program, maybe a little easier to see. Let's walk through it, make it a little bit bigger. So at the top here is something I showed you in Lecture 14, is the exception vector table. It says, at the beginning, just go off to start, and that's the main program. At address 18, there is a branch to the IRQ handler, as I described in Lecture 14. So this is what this tells the processor, go there when the interrupt occurs. But we have to enable it. And so what's going on here? Well, let's look at each thing here. The first thing it does is it actually switches the processor into the IRQ mode. Why does it do that? Actually, it does it in a two-step process. It could have done it in one. These codes have the interrupts turned off. The I bit is set to 1, which means the interrupts are off. Switch me over to the IRQ mode. Set the stack pointer of the IRQ mode stack register. Remember, the IRQ mode has its own stack register, so we must set it explicitly. So we're going to put it up at 40,000 hex, which is a different place than we normally put the stack pointer. Then we move back, and we can change to the supervisor mode. This is the 5 bits describing the supervisor mode, still with the interrupts disabled. And we'll set the stack pointer to be 20,000. That's a different stack pointer. When we change modes, we have a different stack pointer. Spend a lot of time talking about that. This code says, go off and configure the GIC. Don't need to know about that. This code says, I want to access the key interrupt, the key parallel port. And in particular, I want to turn on interrupts for all 4 bits of the interrupt mask register. So this sets the interrupt mask register to be, the last 4 bits are 1, which means every key should cause an interrupt. This sets up a variable called, a word in memory called LED value, to remember what we want the next LED value to be when the interrupt happens. And we initialize it to be 1. And we store that into the LED data register, which turns on the first LED, and we store it in the variable. And then the last thing we do is in supervisor mode. So this is still supervisor mode. See the I bit here? It gets turned to a 0, which means enable interrupts with respect to the processor. And here we're doing it in 2 steps. We could do it in 1. And then we just go into this main loop, which doesn't do anything useful at all. It does a bunch of random ands and ors and just goes around and around and around and around. Because the only thing we're going to do in the interrupt service routine is make sure that it was a key that was interrupting us, and then we're going to change the LED. So here's the IRQ handler, which pushes the registers that it's going to use and the link register, as I've described. Here it's loading the ICC IAR to look at, it gets the address of the ICC IAR and then loads that into register R5 and checks to see if it's equal to 73. If R5 is equal to 73, well, if it's not equal to 73, this is where we freak out. So it stops. It goes into an infinite loop if R5 is not equal to 73. But we arrive here if the ICC IAR is equal to 73, which means it was the key. It was a key-based interrupt. In which case, we branch off to the key ISR, and that's the thing that's going to flip the LED. So you can look at this and see how it flips the LED. But it does something else first, actually. In the key ISR, it reads the edge capture register and then stores it back into the edge capture register in order to turn off any cause of the interrupt. That causes that 1 to be written back into it. And then this code here, I won't spend a lot of time on it. This simply changes the value of the LED to be the opposite of what it was by looking at LED val. And then it returns back here. And here you can see the other things. Here we are writing what was in R5, which has that 73 in it, back into the EOIR, the thing that sends the message to the GIC, got your interrupt, please turn that particular one off. If you have another one, you can leave it on, but turn that particular one off. Get everything back off the stack that you stored, and then the magic return from interrupt instruction, subtract 1 from LR, which I talked about early in this lecture, and plop it into the PC, but also copy the SPSR IRQ back into the CPSR, changing the mode from IRQ. When we landed in the IRQ handler, by the way, we were automatically from hardware in the IRQ mode. This, with a copy of the SPSR back into the CPSR, turns us back into the old mode, the old enabled, the old enable bit. Oh, one thing I didn't say, I forgot to say actually, when you arrive here, the interrupts are disabled instantly. I never said that actually. The I bit in the CPSR gets turned off because otherwise it would just interrupt the interrupt. So that gets turned off. But when you turn this, when you send this back, copying the old SPSR into the CPSR turns it back on. All kinds of things happen with that copy. So a lot going on in this. Everything else in here, there's lots and lots of code. This is the config interrupt stuff that you don't really have to understand. So the program itself is relatively short. So that's the program. And one thing you could do if you wanted to see, which I was doing earlier, you can run this program. Is it running? No. When you continue, when you hit any button here, it doesn't matter which one you turn off. It flips the LED here. Hopefully you're looking at that. One thing you can do, by the way, just to see this happen, let's stop this program. Let's set a breakpoint right here at the beginning of IRQ handler, and let's continue. And you can see execution of this useless main program is happening. But when I hit stop, sorry, not stop. When I hit a key and release it, I hit that breakpoint. And it does, you can watch it do all the things it's supposed to do. So just proving that the interrupt actually happened. Okay, that's the end of this lecture. It's a long lecture. I apologize for that. But I will post this code, which you'll be able to use in Augment for Lab 4. And that will help you do Lab 4. So good luck. Remember, Professor Brown is lecturing all next week. And I'll see you after reading week. So good luck in Lab 4.